Hello and welcome back to Raw Maths. Today we're going to have a look at this question. Now this question actually comes from a set of problems known as the Jewish problems. Back in 20th century Russia, early 20th century, at the State University in Moscow, they actually had some harder question sets that they set for Jewish students in particular in order to keep them out of the university because they did not want to be educating so-called undesirables like Jews and others. So they set these really difficult problems, which have quite elegant solutions often, in order to essentially keep out these people that they didn't want to be educating. So there's a really interesting history behind these problems. I recently found a PDF online of some of these old problems, and I've been giving them a go, and I think they're quite fun. So let's look at this type of this equation here. So problem number 5 says solve this equation: sine to the power of 7 plus 1 over sine to the power of 3 of x equals cos to the power of 7x plus 1 over cos to the power of 3x. First thing I'm going to do is I'm going to rewrite this as just s to the power of 7 plus 1 over s to the power of 3 equals c to the power of 7 plus 1 over c to the power of 3. And the reason I'm doing that is just to make it much easier for me to write, rather than having to write all the i's and n's and x's and o's and s's. I'm just going to write s as sine and c as cos, and of course s squared plus c squared equals 1. So sine squared plus cos squared of x equals 1. Okay, now that's out of the way, I can write things a lot faster. What I'm going to do is I'm going to rearrange this slightly. I'm going to make it look a bit like this. So I'm subtracting the 1 over c cubed, and I'm going to subtract the s to the power of 7 over to the other side as well. And now when I've got a fraction minus or plus another fraction, I'm going to basically cross multiply this and multiply these two together as well. And that's going to give me, well, that's c cubed minus s cubed over s cubed c cubed is equal to c to the 7 minus s to the 7. So this is what I've got so far. It still doesn't look very doable, although I wonder if I can factorise this numerator over here. So I wonder if I can do c cubed minus s cubed. Well, that's going to be, just from knowing the patterns of how polynomials factorise, I reckon c minus s is a factor of this. Well, c is going to have to multiply by c squared to get to c cubed. Then I'm going to have a factor of minus sc squared. So I'm going to need to cancel that out essentially. So I'm going to add in an sc in the middle, because when I multiply this sc by the c, I get plus sc squared. So that's going to cancel when we expand it out, and then I'm going to have a plus s squared on the other side. That s squared times by this negative s gives us this negative s cubed. And let's just check I've done this correctly. So let's expand it out. This is going to give me, of course, c cubed. This will give me plus sc squared, and this will give me plus s squared c. Then I do my minus s times c squared will be minus sc squared. Minus s times sc will give me minus s squared c, and we're looking good so far. And then this is going to give us a minus sc cubed. And now, as you can see, plus sc squared minus sc squared plus sc squared minus, s squared c minus s squared c. And this is simply c cubed minus s cubed. So we're good so far. We've just factorised this polynomial. Now, can we factorise this polynomial? And this is the one that's going to take a bit of work. So c to the power of 7 minus s to the power of 7. Let's see if we can factorise it, and then we'll come back and do some stuff here. So what I'm going to do is I'm actually going to set this up like it's a algebraic division. So c minus s is probably my factor here, and here's my big old bus stop, and I'm going to write c to the power of 7 plus s to the power of 7, and I've left a huge space in here because this is really going to be plus 0c6s plus 0c5s squared plus 0c4s cubed plus 0c3s4, sorry that's not an s, s4, and I'm actually going to need some more space still. Let's keep going. plus 0 c squared, s to the power 5, plus 0 c s to the 6, plus then my s to the power of 7. I'm going to put in black. So everything in red really isn't actually there. I've just added it in the middle to make my polynomial kind of work. And in fact, I just realised this is meant to be a minus, I think. Let me just check that. Yeah, c7 minus s7. So here's my polynomial, and I'm going to just divide through by c minus s. So the way algebraic division works is you say, well, let's take my first term, c. How many of these go into c to the power of 7? That's, of course, c to the power of 6. Then I take my c to the power of 6, and I'm going to multiply by the c and by the negative s, and basically subtract that off on the bottom. So c to the 6 times c is c to the 7, minus, then we've got c to the 6 times negative s, is going to be s c6, or I'm going to write that as c6s. And that's 1 c6s. I take this and I subtract it off. Now what am I left with? Well, let me just tidy up slightly. What I'm left with is c to the 7 minus c to the 7 is 0, and 0 minus minus 1 of this c to the 6s term, that's just going to give me c to the 6s. And in fact, I'm going to write that in black. And I've still got 0 of these guys. And so it looks a bit like this. Now I do that again, I ask myself, how many times does this first term c go into c to the 6 times s? Well, that's going to be c5s. So I'm going to add c5s, and I'm going to do the same thing again. I'm going to multiply my c5s by each of these terms in here, and I'm going to get c to the 6s minus c5s squared. And so when I subtract this off, I'm going to get c to the 6s minus c to the 6s is 0. 0 minus minus, that's a 1, c to the 5s squared. That's going to give me just c to the 5s squared. And I'm not going to bother writing out the middle terms here. I'm just going to write a minus s to the 7 on the ends. And actually, there is a pattern here. So each time I'm just doing 0 minus minus 1 of each of these terms. That'll be c to the 4s squared, and so on and so on and so on. And so actually my end result here, and you can work this out if you want to, is going to follow this pattern: c cubed s cubed plus c squared s to the 4 plus c s to the 5 plus s to the 6. And if you want, you can go through and expand this out, multiply this polynomial on top by this one down here, and figure out what this is. For now, I'm just going to call this p. So this is our new polynomial up here. Now let's go back to the question that we had, the stage that we had kind of here, right? So let's take this part of our equation and just figure out what that is going to become further down. So let's just go all the way down here, and this was, hang on, c cubed minus s cubed over c cubed s cubed over c cubed s cubed is equal to, that was c to the 7 minus s to the 7. We've now said this is equal to c minus s brackets c squared plus cs. I'll write an sc instead, plus s squared over c cubed s cubed equals c minus s. And then we've got this huge thing, which was c6 plus c5s plus c4s squared plus c cubed s cubed plus c squared s to the 4 plus cs to the 5 plus s to the 6. Okay, now we've got the same factor on both sides. We've got this guy and this guy. And so, well, what can we do there? We can say this equation holds true when this bracket, c minus s equals 0. Therefore, just remember we've got c and s are, that's cos of x minus sine x equals 0, or in other words, cos x equals sine x. So this whole polynomial at the top here, sine 7 plus 1 over sine cubed equals cos 7 plus 1 over cos cubed, well, that is simply going to hold true when cos x equals sine x, and that's trivially true, right? That we can actually notice that just from the get-go. If sine x and cos x are the same, then both sides of these equations have the same format, and so we didn't actually need to do all that working to find this particular solution, but we will need to keep on with this train of thought to find any other solutions that there may be, or to rule out there being any other solutions. Now, this is of course true when x equals pi over 4, or, well, sine looks a bit like this, and cosine looks a bit like this. So when are these two graphs intersecting? Well, there's this one at pi over 4. There's also this one. If this is pi, then that is pi plus pi over 4, which is of course 5 pi over 4. So here's two solutions right here. Now we need to find, are there any other solutions? So now I'm going to go back to this equation, or this step, and I'm simply going to cancel this out. I'm going to divide both sides by c minus s, presuming it's not equal to 0. So if c is not equal to s, then I'm going to cancel that out, and then I'm going to see what do we get. Now, for this step of the workings, I'm going to do something. I noticed there's lots of s's and c's multiplied together, right? There's quite a lot of those, and so I'm just going to let, let's say t equals sine x cos x. This is going to be my substitution, and that's just sc, right? So let's write out this equation above, but using t instead. Well, I'm going to get, on the left-hand side, that's c squared plus t plus s squared over t cubed equals, on the right-hand side, ignoring out my cancelled out term here, I'm going to get c6 I can't really touch, and I'm going to group that with the s6 here as well. Then I'm going to get c to the 5 times s. Well, that is equal to c to the 4 times t, right? Because t is cs or sc. And so I'm going to get plus t times c to the 4 plus, same thing here with the s to the 4 term, here with the s to the 5 term, that's cs. Well, cs is t, and then you've got 4 s's left over, that's t s to the 4, plus then I've got, so I've done this, I've done this, I've done this guy and this guy, then my c to the 4 s squared is going to be t squared c squared, plus I've got this one, which is t squared s squared, because again t is cs, so t squared is c squared s squared, and I've got 2 s's left over. And then I've got this in the middle, which is my last one, which is c cubed s cubed, that's simply t cubed. Now, can I group some stuff? Yes, I can. I can say c to the 6 plus s6. I'm going to just group that in some brackets just for notation's sake. I'm going to say t, that's c to the 4 plus s4, factorise that, plus t squared, c squared plus s squared, plus t cubed. Now I've got some relatively simple sort of polynomial terms here, and I can figure out what each of these is. Well, straight away this is just 1, because cos squared x plus sine squared x is 1 by definition. That just follows from Pythagoras. And similarly, I've actually got the same thing here, c squared plus s squared. And so I can say, well, on the left-hand side, that's 1 plus t over t cubed equals, on the right-hand side, I don't know what these guys are yet, so c to the 6 plus s to the 6 and c to the 4 plus s to the 4, but I'll just write out those, c6 plus s6 plus t times c to the 4 plus s to the 4 plus, well, this is t squared and this is t cubed, plus t squared plus t cubed. Okay, this is what I've got so far. Now let me figure out each of these in turn. I'm going to start with the smallest one, because the smallest one will help us figure out the larger one as well. So, c to the 4 plus s to the 4. It would be really nice if I could factor out a c squared plus s squared. Reason being, this is of course equal to 1. Again, because cos squared plus sine squared is 1, no matter what the x is. So let me take this and square it. And what does that become if I just square this guy? That becomes c to the 4, which we want, which is good, plus 2 times c squared s squared plus s to the 4. So if I take c squared plus s squared squared minus this term here, which is in reality 2t squared, because again t is cs, that is going to equal to c to the 4 plus s to the 4. Now this is really, again, c squared plus s squared, this is equal to 1, and therefore we're going to get 1 minus 2t squared. So this is really what should go in this bracket in terms of t, is 1 minus 2t squared. Cool, that's interesting. Let's do the same thing with c to the 6 plus s to the 6. So let's say c squared plus s squared. That's hopefully going to be a factor. Let me try multiplying that by c to the 4 to get that c to the 6 term. Now I'm going to have to take off an s squared somehow. That's going to be minus s squared c squared, perhaps. This is going to multiply there to make an s squared c4, which is what I want to take off when these two multiply together. Then I'm going to add on an s to the power of 4. And let me just check if I've done this correctly, because I'm not actually sure. That's going to be c to the 6 by multiplying these. Multiply these, I get a minus s squared c to the 4. Multiply these, I get plus c squared s to the 4. So that's looking good so far. Multiply these, I get plus s squared c to the 4. And is that correct? Yes, sorry, I've written around my c and s's the wrong way around there. Yeah, that's correct. Multiply these, I get minus s4c squared, and then multiply these, I get plus s to the 6. Now what happens here? Well, minus s2c4 plus s2c4, they cancel. Plus c2s4 minus c2s4, they cancel as well. And yes, this is c6 plus s to the 6. That's all that's left over. So I have factorised this correctly. Now this is useful because this equation here, well, this is 1 times c to the 4 plus s to the 4 minus s squared c squared is just t squared. And that's useful because the 1 doesn't matter, that's just multiplying by 1 is it just gives you the identity. So c to the 4 plus s to the 4, we decided this was 1 minus 2t squared minus another t squared, which is 1 minus t cubed. Okay, now why did we want both of these? Well, it's because this goes in, that will go in there. And so really our equation at the top, which was here, this equation, really rearranges in terms of t to be 1 plus t over t cubed equals c to the 6 plus s to the 6, that's 1 minus t cubed. Then plus t times 1 minus 2t squared. Hang on. I don't know why I've written this. That's not t cubed at all. That's 3t squared. And that is 3t squared there as well. That's embarrassing, isn't it? There we go. 1 minus 3t squared. 1 minus 2t squared there. Then we've got plus t squared plus t cubed. Now let's tidy this up a little bit. Let's say that's 1 minus 3t squared plus t minus 2t cubed plus t squared plus t cubed. That's going to be the 1. Minus 3t squared plus t squared is minus 2t squared. We've got plus t, we've got minus 2t cubed plus t cubed is just minus t cubed. Let's add everything over onto the right hand side to make it all positive and make a polynomial equaling 0, that's going to be a t cubed plus 2t squared minus t minus 1 plus that 1 over t cubed phrase equals 0. Now multiply through by t cubed to get rid of this denominator here. We're going to get t to the 6 plus 2t to the 5 minus t to the 4 minus t cubed plus t plus 1 equals 0. And again, just a reminder that t is equal to sc, which is in fact sine of x times cosine of x, or we can write that as sine of 2x over 2. That's going to be quite useful. Okay, does this polynomial ever equal 0? If it does, we can then resub our sine x cosine x or sine 2x back into this and figure out what x would be in that case. If it doesn't, then we know there's going to be no more solutions to our original problem. So does this ever equal 0? Well, let's figure out what the range of t is. So, well, t is sine of 2x over 2, right? If I draw a graph of what that looks like, well, sine of 2x is going to be a bit like sine of x, but more like this, right? So quite a high frequency compared to sine of x. So this would be pi just there. So divide by 2, that's going to decrease the amplitude, which is going to look like that, right? So this is sine of 2x over 2. So same frequency as sine of 2x, but the amplitude is halved, which means the maximum value, this peak here, that is going to be 1/2. Well, this is 1. And the minimum value here is going to be minus 1/2. And this is minus 1. So t is actually bounded by between 1/2 and minus 1/2. So where does this equation go? Does this equation ever actually equal 0? Well, let's try some stuff. Let's put in t equals 1/2 to see what that looks like. T equals 1/2. We're going to get 1/2 to the power of 6 is 1 over 2 to the power of 6, which is 64, plus 2 over 32, minus 1 over 16, minus 1 over 8, plus 1/2, plus 1. This is going to equal, these cancel out because they are the same thing. That's 1 minus 8 plus 32 plus 64, all over 64, just giving a common denominator to all the fractions and adding them all together. And that's going to be 1 minus 8 is minus 7, 32 minus 7 is 25, 64 plus 25 is 89 over 64. So when t is 1/2, our polynomial works out to be 89 over 64. What about t is minus 1/2? Well, we're just going to flip the sign on a few of these with odd powers. So it's going to be, we're going to get 1 over 64 still. That's going to be minus 2 over 32, minus 1 over 16, plus 1 over 8, plus, sorry, minus 1/2, plus 1. And that's going to equal, again, putting a denominator of 64 in everything, it's going to be 1 minus 4 again, plus 8 minus 32 plus 64 over 64. Minus 4 plus 8 cancel out. 64 minus 32 is 32, plus 1 is 33. That's 33 over 64. Okay, interesting. So t is 1/2, we get this positive number. T is minus 1/2, we get this positive number. T equals 0 then. So t equals 0, well, trivially, these terms all become 0, and this is just 1. So we get 1. So no matter what number of these we put in, we actually still get numbers that are greater than 0. So does this ever actually touch 0? Well, it doesn't look like it. Here it is. This is y equals x to the 6 plus 2x to the 5 minus x to the 4 minus x to the 3 plus x plus 1. And we're really interested in the range between minus 1/2 and plus 1/2. So just down here and here. And you can see this never equals 0. 0 is down here. The root of this equation is actually here, so minus 0.77 or so. And in fact, that is outside of our suitable range for t. t is never going to go down to this point, or domain I should say. T is never going to go down to here. It's bounded at -half and a half because it is sine of 2x over 2. So this function never crosses the x-axis between in the correct domain, and therefore we actually have no solutions to this polynomial just here. Which means our only solutions to this question are these ones: x equals pi over 4 and x equals 5 pi over 4, within, of course, the bounds 0 to 2 pi. Within those bounds, these are our only correct solutions. There's actually infinitely many solutions if you extend that domain. Okay, so our solution here is x equals pi by 4, x equals 5 pi by 4. Very simple solution, and actually interestingly, these so-called Jewish problems set by Moscow University to exclude Jewish students from admission, they actually often had very simple solutions, and so they could say that no, we're not discriminating against Jewish students because look how simple the answer actually is, you just couldn't figure it out. But as we saw, the actual steps needed to get there are pretty extensive. So I hope you enjoyed that question. I'll be doing more of these Jewish problems in the coming days and weeks because they are very interesting historically and mathematically. So stay tuned for that, and I'll see you in the next one. Thank you very much.